Hello, class. So we are on section 3.2 now, which is about polynomial functions. Okay, so we already know about polynomials from section 1.3. So I would like you to recall section 1.3, which literally I think I called polynomials. Okay, so a polynomial of degree n, okay, will look like this. So I'm going to have p of x for polynomial. And it's going to look like a sub n, x to the n, plus a sub n minus 1, n minus 1, plus dot, dot, dot forever, a2x squared, a1x plus a0. And so hopefully you remember this is what a polynomial looks like. And you're like, okay, this is the leading coefficient. This whole thing is the leading term. N is the degree. And then, right, like, so it kind of matches, right? So you can put an invisible 1 here if you really wanted. And then technically, there's an invisible x here with a 0. You can imagine those. All right, we just customarily don't write them down because this one is the constant term, which normally we just like know it because it doesn't have the x. Okay. So if you could tell, kind of the middle part here, right, doesn't have any special names, so it's not really that important. And if you look, the leading term is actually the most important, and so this is true. Okay, so now we're gonna graph some polynomials, right? So last section we graphed the quadratic. Way back in chapter 1 we graphed lines, which are linear polynomials. Now we're gonna know how to graph the rest, or at least we're gonna try. Okay, so polynomials, one of their key features is that they're smooth and continuous. Okay, this is one of the, well, these are two of the things that make polynomials kind of nice and special. Okay, that they're smooth and continuous. Okay, so here's examples of stuff, right? If you remember, this is the absolute value function. This is not a polynomial because it's not smooth. Okay, it has a corner right there at x equals 0, right? Whereas x squared is a polynomial and it is smooth. Okay, and then right, anything like the reciprocal function or stuff like that, right? This is not continuous because you have to pick up your pencil. Okay. All right. Now I want to talk about something a little bit complicated. And you kind of do need calculus, but we're gonna just use words instead of calculus. Okay. So I'm gonna talk about end behavior. Okay. And it's kind of what it sounds like. What's end behavior? It's what happens at the end. Okay. So I would like to say it's the arrows, right? We always draw arrows on our graphs, right? That's the end, right? Because then it just, right, the arrows just mean you go off forever, but you kind of know what that means, right? So end behavior is the arrows, or what happens, right? It's what happens as x goes to infinity or goes to negative infinity. Okay. And polynomials have very specific end behavior that makes them nice. Okay, so here, right, I have x squared. And then here, I have x to the 4th. And then here, I have some function, I don't know. Okay. But it's like a fourth degree polynomial. And then here I'm gonna like some crazy sixth degree thing. Okay. And we notice, so like x to the sixth plus stuff, and x to the eighth plus stuff. Okay. So I hope you guys notice that they all kind of look sort of the same here, right? And that's true with x cubed, right? Because then x to the fifth looks like this. Some different kind of x cubed will look like this. And then let me get like x to like the seventh in here. Okay. And so you notice there's like two patterns, right? If your degree, if the leading term, right, is even, you're gonna look like a U or a W, right? But if your leading term is odd, you're gonna look like sort of the cubic function, right? Or some kind of n thingy. Okay. And so this is true. This pattern holds up, and it's actually called the leading term test. Okay. So the leading term test is what tells you n behavior. Okay. So there's this table. Well, there's like a chart. Okay, so okay, so um we're gonna look at the degree. Okay, so let me do this differently. The degree, and if the degree is odd or even, something happens. And then over here, this is gonna be the lead coefficient. And if it's positive or if it's negative. Okay, so these are the four things that affect n behavior. What's your degree? Is it even or odd? And what's your leading term coefficient? Is it positive or negative? Okay, so if your lead coefficient is positive and you're odd, the arrows are gonna start down, and then some stuff happens, and it's gonna go up. Okay, but if your leading term is positive but your degree is even, then you're going to start up and you're going to go back up. Okay, and that's kind of what I showed you here, right? The arrows here both always pointed up, and the arrows here it started down and then went up. Okay, so that's what happens here. And the opposite thing happens because like reflections, right? If we remember the transformation section, basically this means I have to flip it. So if the leading coefficient is negative, then I start up and go down for odd degrees. And then for even degrees, that means I'm just completely upside down. So they both go down. Okay. And so the math way to talk about this, so I'm going to talk about this one. Okay. You would say as x goes to negative infinity, okay? And basically what that means is as x goes left. Okay, so if we follow to the left, what happens? We go down, right? You'd be like y goes to negative infinity or down. Okay, and then as x goes to infinity, right, which just means right. Okay, as x goes right, y goes to infinity, which here this just means up. Okay, so this is the math way to say what the arrows are doing. Okay, down means negative infinity, up means positive infinity for y. Okay, y is the up and down. And then x, negative infinity means left, and positive infinity means right. And then x is left, right. Okay. So let's do an example. Okay, so I just want you to tell me, here's a function. Okay, 2x squared minus 3x plus 5. All right, so I want to know what is the end behavior as x tends to negative infinity. Okay, so the question is basically like, what happens when x goes to the left? Okay, so if we do the leading term test, right, we are even degree, and positive coefficient. So that means we look like this. This is our end behavior. So then x tends to negative infinity. That means left. So this. Okay, so here are all the possible ways you can answer this question. Okay, if you say the word up, that's okay. If you say positive infinity, that's okay. If you say infinity, that's okay. If you write down the word infinity, that's okay. If you put an up arrow, that's okay. If you put this kind of arrow, also okay. The best answer would be to say y goes to infinity. This is the best answer, okay? But all of these acceptable answers, okay? What you can't say is blows up, okay? You can't say blows up or explodes or any of those. Obviously, if you said down or put a down arrow, that would just obviously be wrong, okay? But yeah, any of these would get you full credit, okay? With this one being the best. But end behavior, not that complicated, okay? So let's just do one more. Okay, so I want to know end behavior of p of x equal to negative 7x cubed minus 2x plus 1. Okay? As x tends to positive infinity. Okay? So we look at the leading term. It's odd and negative. So that means we're going to look like this, right? This is our end behavior if we do the leading term test. So then I want to know what happens x goes to infinity, which is right. So this. So then answer down. Negative infinity. Y goes to negative infinity. Okay, all of those. Okay. But there you go. Leading term test and end behavior, not that bad. Okay. Moving on though. Okay, so now we're going to talk about really arguably the most important part in the entire chapter. Okay. We're going to talk about zeros. All right, which are also known as roots. Okay. So if x equals c, okay, so if we have a number and we plug it in and we get 0, then c is a 0. All right, so a 0 is just what we call numbers that when you plug them in, make the polynomial 0. We also call them roots, okay? Or I guess root, because singular, right? Like roots, zeros, okay? All right, so there's many different names and many different ways to answer the same question, okay? So I'm going to write down 4 basically the same sentences, okay? So you can be like, C is a 0, okay? Makes total sense. You can also say x equals C is a solution of the equation equation, P of x equals 0. Okay, which this is really that's how we find zeros, right? Is we do number 2, right? The other thing you can do, which I think you guys have noticed, right, is if you factor, if you have x minus c, most of you can tell me that c is the 0, right? So x minus c is a factor of p of x, okay? And this is actually like a super complicated topic, like 400 level math, about what like factors and zeros and how they're related and all that kind of fancy stuff. And then one more is c is an x-intercept of the graph of p of x. Okay, so the zeros are also where you cross the x-axis or touch the x-axis. Okay, so with all of this zero stuff, we can now start graphing. Okay, so graphing polynomials. All right, so first of all, if the polynomial is degree 1, then it's a line. And you know how to graph those. Just use slope-intercept form, okay? If the polynomial is degree 2, we just learned how to graph those. Use vertex form. Okay, this is for polynomials of degree 3 and bigger. Okay, so when we graph, we're gonna follow a kind of like a flow chart, okay? Step 1 will be to factor if it's not already factored for us, okay? Because we want to find the x-intercepts, which are also the zeros, okay? So step 1 is find the x-intercepts or zeros, and that normally means we're going to factor, okay? Step 2, after you find that, would be you want to find the y-intercept, okay? Which this is not that hard, because you just plug in x equals 0, okay? So step 2 is find the y-intercept. Step 3 is you need to know end behavior, which is why I taught you this at the beginning of the section. Okay, you need to know where the arrows go. Okay, and then so like I don't know end behavior. Okay, and then step 4, the last step, is you connect the dots. Okay, or you can start plugging in a whole bunch of numbers, right, from previous sections, right? You can always just make like a little table and just start plugging in numbers that you want. Okay. Kind of important though, when you connect the dots, remember that polynomials are smooth. Okay, so you cannot connect the dots and there be corners anywhere. Okay. All right. So let's start graphing. Okay, so I'm gonna start with this example. Okay, so here I have x plus 2, x minus 1, x plus 3. Okay, and it's already factored for you. Okay, so couple of things, right? So let's go down our chart. Since it's already factored for us, we know the zeros, right, are -2, 1, and -3, right? Because it's always the opposite. Right, you could just plug them in and see. Okay. So then step 2 is I want to find the y-intercept. Okay, so what do? I just plug in 0. So what happens? I'm going to get 2 times -1 times 3, which is -6. So the y-intercept is 0, -6. Not that hard, okay? Now, step 3 is end behavior. Okay, so something you could do, but I don't advise, is you would FOIL all of this together. Okay. I would not advise that just because that takes a lot of time and you could mess up. Okay. So to find the end behavior, remember, we really only care about the leading term. And a secret to just getting the leading term is kind of to just do the F in the FOIL. Okay. So what do I mean? Is you just multiply these three together. Okay. And then so you can say that P of X has leading term X cubed. Okay. Which that's all we really care about. Because then we see that the leading coefficient is 1 and the degree is 3. So this will have end behavior this. All right. And then step 4 is we graph. So let's graph. Okay. So let me get a graph here. Okay. So zeros. Okay, so I'm gonna try and be evenly spaced. This is gonna be difficult. Okay, let me. Okay, so 1, 2, 3, 4, 5, 6. Okay, so I'm gonna put my dots everywhere. So this is the y-intercept. Here is the x-intercept. I need one more. 3. Okay, and then this is my end behavior. So I know I start with an arrow down here and I end with an arrow up here. So now I just connect the dots. So I'm just like, okay, I'm gonna do this, and then I'm gonna go here, and then I'm gonna go there, then I'm gonna go, maybe I should a little more smoother. And there you go. Okay, ta-da! It's been drawn, okay? And then, just to show you, this is good enough, all right? This is what math people would call a sketch, okay? Because really, the only numbers I really know are correct are these intercepts. 1, 0, -2, 0, -3, 0, right? Like all of these numbers could be slightly off, but it's gonna look like this, okay? So math people call this a sketch, okay? Not really a graph. But if you want, we can go on our favorite graphing software known as Desmos, and we can see what this looks like. So let's type this in. So x plus 2, x minus 1, and x plus 3. Ta-da! And you see, yeah, it kind of looks like what I drew, right? Here you have the x-intercept, -3, 0, -2, 0, 1, 0, and the y-intercept, -0, -6. Okay? And it, right, the arrow's pointing down here, and it ends up there. And so good enough, all right? The sketch is good enough. Now, so this is how we graph polynomials, okay? And so let's do some more examples, okay, as they get a little more complicated. So here, example. So I'm gonna make this one just a little bit harder. So this minus x plus 7, 5x minus 1. Okay, so this just looks like a mess, right? All right, but we can graph this. Okay, so step 1, what are the zeros? So you actually have to solve them because they're a little annoying, right? So this 0 is gonna be -3 over 2. This one's gonna be negative, no, it's gonna be positive. Positive 1/3. This one's gonna be 7. This one's gonna be 1/5. Okay, so those are the zeros, right? And if you're a little confused, you know, always, you can always just solve it like this. Okay, that's what I did for all of them. Move that there. Okay, so the zeros, which are the x-intercepts, -3/2, 1/3, 7, 1/5. Okay, so they're like kind of jumbled. All right, 2 y-intercept. Okay, so what happens when I plug in 0? I'm gonna get 3 times -1 times 7 times -1, so I'm gonna get 21. So the y-intercept is 21. Okay. And then leading term test, right? I need to do the leading term test to get n behavior. All right, and then here's where again I would, right, as they get bigger, you really don't want to FOIL everything out. So I'm just gonna multiply these 4 things together. So 2x, 3x, -x, 5x. And I'm gonna get 30, -30, x to the 4th. So that's my leading term. So if I do leading term test, I know since I'm negative and even, my n behavior should be like the upside down U thingy. Okay. So now this is all the info I need, really. I probably, you know, I should plug in some points maybe, but if I were to make a graph, okay. So I'm gonna go -3/2 is here. 1/3 is, I'm gonna put it there. Except no, because 1/5 is smaller than 1/3. So 1/5 goes there. 1/3 goes there, and 7 I'm gonna put way over here. Okay. And the y-intercept is 21. So I'm gonna put that way up there. Okay. Put some dots. And I know by n behavior, right? N behavior, both of my arrows are down. Okay, so I'm gonna go here, and then I go up here. I'm gonna go this. Ta-da! Okay, so all right, and this is a really weird graph, but it's gonna be close enough, right? So let me smash this into Desmos and see how close my sketch is. Okay, and it's gonna be really off just because the numbers are really different. So like it's gonna, like, mine looks probably really morphed around. 3x minus 1. Okay. -x plus 7. Okay. And then 5x minus 1. Ta-da! So it looks bad. Did I type this in here? Right? What is happening? I am highly confused. So apparently it blows up pretty nasty. Like very nasty, because I'm in the hundreds and it's still going up here. Oh, but the first hump ends at like 193. Okay. And even though it looks pointy, guys, all right, if you zoom in enough, look, it's smooth. Okay, smooth. No corner. Okay. It just looks pointy because we're way up here in the 190 somethings. When does the other thing stop? Way up here. So around 8,000 is where the other one finally stops. And you can see it's smooth. right around 8,803. Okay. All right. So this is where you would actually want to plug in numbers if you want to be even, medium, close to accurate. You would have plugged in some numbers. But we don't really care. All right, we just care about the stuff down here. All right. So we see, first of all, we see that the end behavior is they both go down forever. Okay. And then we also see that our x-intercepts are where we think they are, right? This is negative 1.5, which is negative 3/2. This one is 1/5. This one is 1/3. And over here at 7 is my other one. Okay. And we can see that's pretty much it. Oh, and the y-intercept, I guess I could show you. I think I did at the start, right? It's 21. Okay, you gotta do some zooming in, but just trust me, it's 21. Okay. All right. So it doesn't matter how nasty it is, you can get something like this. All right. Okay. Now, let's make it even a little bit harder, but at least prettier. Okay, so example here, this time, we're just going to give you this. Okay. So now, step 1 is more complicated, right? Because now I have to find the zeros. So I have to factor. Okay. And here is where you have to think of me when you're doing these kind of problems, because for any degree bigger than 2, you really only know factor by grouping or this kind of factor where you can just tear an x out, right? So you have to, right, if you are assigned a question, that means I think you can do it. So, you know, you're not going to need to whip out some fancy exotic things that you might Google on the internet, is kind of what I'm trying to say. Okay, so you should totally be able to do this because it factors. You take out the x, and then this thing you know how to factor, right? X minus 3, x plus 1. And ta-da, it's factored. Okay. So then you can tell me the zeros, okay, are 0, 3, and negative 1. And even as a bonus, since this thing, right, since 0 is a 0, the y-intercept is also 0. You don't even have to plug in. Well, you could. It wouldn't be hard. You would see that everything goes to 0. Okay. But that's nice. And then here, well, since I gave it to you scrambled, you could just look at it and tell me the end behavior by the leading term test, right? So it's going to be this. So we can graph this, right? 0, 0, 3. So 1, 2, 3, and negative 1. And then my arrow starts down here and ends up there. So let's connect this smoothly. Ta-da! It's a graph, okay? And let's smash this one into Desmos and let's see if it looks like that. So x cubed minus 2x squared minus x this. Oh, I was like, why am I not seeing anything? Because I'm still go home. Yeah, okay. And ta-da! It looks like what I said. Right, so negative 1, 0, 3. And I mean, it looks like this, right? I guess if you wanted to, now that I know what it looks like, you could be like, you know, there you go. Now it's more accurate. It doesn't look, that looks a little less smooth though. Yeah. This is a little better, but it doesn't matter. All right. Really, all that matters is the x-intercepts. Okay. If you want it to be more accurate though, again, what I would tell you to do is like, right, here's 0 and here's 3. plug in what happens at like 2. What happens at 2? So if you plug in 2, you're going to get 8 minus 8 minus 3 times 2. So you're going to get negative 6. So then at 2, I would be like, oh, here's another point. And that just gives you more dots to connect when you're doing step 4. All right, and now I know, now it's more accurate quotation marks, okay? But really, no one cares. You just need to do x-intercepts, y-intercepts, and behavior, and you're fine, okay? All right, so now I want to introduce one of the last couple examples, okay? Or I want to introduce this example because something weird is gonna happen, okay? So x cubed plus 2x squared plus x. Okay, so you're going to want to factor this, right? You need to factor this. And then I don't know if this looks familiar to you yet. Hopefully it does. But if it doesn't, just try and factor. It's actually this thing, okay? Which is this, okay? So you have 2 zeros, right? Your zeros are 0 and negative 1. The y-intercept is 0, and your end behavior, because this is again a cubic with positive things, so we're gonna do down arrow and then up arrow. So if you try and draw this, right, 0 here at negative 1, right, and you're like down arrow, up arrow, you might be a little confused because you're like, okay, so I'm starting down here, and then I go here, and then you're stuck, right? Because you need to go up here, but you don't have another x-intercept, right? You can't cross, or else technically you'd have another one. So how do you, right? You need to kind of puzzle out, how do I do this, right? And the secret is you go here and you bounce off that one and cross that one, okay? So here you bounce or touch, and at that one you cross, okay? And so how do I know that? Okay, it has to do with this thing, right? The fact that this has a squared on it, okay? And it's called multiplicity. But let me just show you, first of all, that this is correct. So x cubed plus 2x plus x. What? Have I gone, what? Excuse me? Have I gone crazy? X cubed plus 2x plus x. Has Decimals gone crazy? Oh, no, I've gone crazy. There you go. All right, there, and so you see that, like, right, it does. It just goes up there, hits negative 1 at the x-intercept, but it doesn't cross. It just goes back down. And then here, we actually do cross. So that's how you get only 1 0. That's how you only get 2 zeros, okay? All right. So this concept is called multiplicity, which I kind of talked about a little, okay? But multiplicity, okay, is if you get x minus c to a power, so n is a factor, and n is greater than 1, the 0 c, okay? We like to say, so has multiplicity n. okay? So, and some specific stuff happens, okay? So here are the two rules with multiplicity, okay? If multiplicity, okay, so if n is even, okay, then the graph bounces, okay, at C. But if n is odd, then the graph crosses at C, okay? And so the reason we haven't seen this all is because, right, technically all of the examples I've shown you, these all have multiplicity 1, okay, which is the most common, right? You usually just get one of them, and 1 is odd, so that's why we've always been crossing, okay? So, but when you get an even number, right, when you get this, that's when you get the bounce, okay? So let's look at some polynomials. Okay, so here I'm gonna have p of x, okay, example. And it's gonna be x to the 4th, x minus 2 cubed, x plus 1 squared. Okay, so it's factored for you, so we can see the zeros, all right? The zeros are 0, 2, and -1. Right, the y-intercept is 0. And the end behavior, so the leading term, you're going to have to do some serious multiplication here. But it's going to be x to the 4th. Okay, this thing, I'm going to like partially cube. So I'm going to multiply an x cubed here. And same here. Okay, so the leading term is actually going to be x to the 9th power. Okay, all right. With the 1. So since it's x to the 9th power and a 1, we know the end behavior should be this. Okay? And then so if I try and graph this, we're going to get a 0 here. We're going to get a 2 and a -1. And then 0 has multiplicity 4, 2 has multiplicity 3, and -1 has multiplicity 2. Okay, so I specifically know what's gonna happen when I get to my zeros, okay? So I start down here, okay? And I'm approaching -1 with multiplicity 2 though. So that means I don't cross, I bounce, okay? Then I head to 0, which also has multiplicity even. So I'm gonna go back up and bounce off again. And then I'm going to go to 2, which has an odd multiplicity. So that's when I'm going to cross and go up. Okay, so then we get this very weird graph, right? But you can see that knowing the multiplicity is important because here, right, if you didn't know multiplicity, you could have done this. Okay, that would have been more normal looking, right? But then you would be wrong. Like this is very wrong. Okay, your positive and negative signs are flipped. Okay, and then let's graph this in Desmos just so you can see. So x to power 4, and then x minus 2 to power, what did I say, 3, and then x plus 1, 1. Okay, so we see the graph is getting real funky here. All right, it's getting real weird. But this is 2 power 2. So it looks like this, which is weird. But you notice that I'm right. Right? It bounces here, and it bounces here again. All right. I don't know why it looks this weird. That's a good question. And then it goes down. So we see it goes back down. And then finally here at 2, that's where we cross. Okay. And well, okay, so the reason it looks like extra weird It's just because the powers are getting really huge. So it's allowed to be a little funky. All right. Okay. But that's multiplicity. All right, leave. Which is pretty much that's like the end of it. Okay, so let me see. Yeah, okay, this video is getting a little long. Let's just do one quick example, one more with multiplicities. And then let's wrap up this section. So here I'm gonna have an x. Let's do x plus 2 squared, x minus 1 cubed, x minus 3, x, let's do another x plus 1 squared. No, okay, let's make this one 3, and let's make this one like a 2 or a 4. There we go. Okay. I have no idea what this is gonna look like. Okay, so we can see the zeros. Okay, so the zeros, right? It's -2, 1, 3, -1. Okay. This has multiplicity 2. This one has multiplicity 4. This one has multiplicity 1, which we don't really even call it multiplicity 1. We just say 3 is a 0, right? This one has multiplicity 3. Okay. The y-intercept I don't know. I have to figure it out. Oh, and it's gonna be a little bad. Oh, actually, it's not that bad. Okay, so I have to do plug in 0. Okay, so p of 0 is gonna be 2 squared. Okay, notice the powers are doing stuff here, guys. -3, 1 cubed. So that's gonna be 4 times -3, because this is 1 and that's 1. Okay, so that's gonna be -12. Okay, that's not too bad. That's the y-intercept. And then end behavior. Okay, so I'm gonna get an x squared times an x to the 4th times an x times an x cubed. What is that? 4, 8, 9, 10. So an x to the 10. Okay. So my end behavior should be up, right? It should look like a U or like a really crazy W. All right, so if I were to graph this, let me zoom out a little. I'm gonna graph this. So -1, 1, -2, 2, 3. Okay, so let's get these. Okay. The y-intercept is -12. So let's just put that down here. Okay. And I need to know, okay, so I'm gonna bounce here, cross here, bounce here, bounce here. Okay, let's just do it slowly. All right. So again, I know I'm starting up. Oh, I'm starting up. Okay, so up, and then I hit -2, which I'm gonna bounce off of. Okay. Then I'm gonna go back to -1, which I'm actually gonna cross. Okay. Which makes sense because I have to get to the y-intercept. Okay. Okay, so smooth. Also the whole time you're doing this, think smooth thoughts. Okay. I'm gonna go to 1, and that has even multiplicity, so I'm gonna bounce off this one. And then I'm just gonna freestyle this. I know this one has to have odd multiplicity, which it does. And then ta-da. So there's my graph. Okay. A little funky, but you know, it's accurate. It's good enough. Right? Full credit. So let me now graph this on actually, okay, you can graph this on Desmos with your own free time. Okay. I think that's it for this section. All right, see you guys in the next section.